Welcome to Power System Protection course. We will start a new module on wide area measurement system based protection, where we will discuss on different lectures how the PMU technology can be used to have wide area measurement system which can be used for protection application. In the first lecture here, we will see the basics on what phasor measurement unit or PMU is, and then we will go how the wide area measurement system can be achieved, and in subsequent lectures we will go for different applications on protection related perspective. We know phasors, we have dealt with these in all the relays. We started with phasor estimation, and then how the based on the phasor estimation the phasors, voltage, currents, and then went for the sequence components which are being widely used for different protection applications, directional link, differential link, distance relay, and so. So, revisiting on that, we know for an electrical circuit AC system, Vm cos omega t plus phi voltage input, current in the circuit, let us say this is an RL circuit. So, to analyze this in a steady state, we transform the circuit to the frequency domain, where you can write the corresponding R and the reactance parts j omega L. Then we represent the corresponding sine or cosine voltage as phasors, V with an angle of phi, and V upon the corresponding impedance in terms of R plus j omega L, we find the I. So, this I becomes a phasor with having certain angle based on this voltage angle and the corresponding impedance angle. So, what you do from the time domain, we go to the phasor domain and analyze the behavior of the circuit. So, that analysis in frequency domain gives us the concept of phasors, because here in the frequency domain these voltage and currents are represented by phasors, 50 hertz or 60 hertz component. So, for that what do you do, that the corresponding sinusoidal quantity of voltage we represent that as a phasor which rotates anticlockwise with a speed of omega 2 pi f, and then from there you can say that we obtain the corresponding current which also rotates in anticlockwise direction with respect to the voltage. So, relative angle between voltage and current remains same till there is no change in the circuit condition or so. Moving forward, now let us think that two phasors when you require at two different locations. So, these are two substations remotely connected by any transmission line which having an impedance of Z say. So, we write the corresponding equation of this one in terms of V 1 minus V 2 equals to I Z. Here in all these voltages and currents are phasors, and we can write the corresponding relations from which we talk about that the impedance Z parameter can be obtained or so and so. If two are given, the third can say that can be obtained, third phasor can be obtained also. So, that means that if you represent these phasors from this corresponding voltage signal here, let us say V 1 here and V 2 here, and if you like to have V 1 minus V 2, the corresponding phasor here will be V 1 and corresponding phasor will be V 2. But now the question is that how to get this V 1 minus V 2, because this is having a time axis here and this is having a time axis here, and this device is at remotely placed from the other device where the measurements are being taken. So, the clock of this which decides this time axis of here for this phasor for this waveform and the clock of this measurement stations 2 decides the corresponding time of this waveform and the associated phasors, they must be same. Then only we say that these two phasors can be plotted in one go. It means that the corresponding two waveforms, blue one left hand side and the red one on the right hand side, this would have the same time axis. It means that either they should have the same clock, which in this case seems to be impossible because they are maybe hundreds of kilometers away. Otherwise, they should have a one, you can say that time reference from which the corresponding device should get the time information. Then only you can say that the two waveforms would have the same time axis, then only we can draw the corresponding phasors in one plot. If so, then we can have a meaningful comparison, then we can write V 1 minus V 2 or V 1 upon V 2, and so we can play with the phasors. Otherwise, from the basics fundamental of theory, it is not possible. So, in this perspective, now these two time information of these two devices at location 1 and location 2, if they have an error of 1 millisecond, that may lead to 18 degree, because 1 millisecond we have know 360 degree upon 20 millisecond per cycle leads to 18 degree of error. And if they these two time information of the two devices will having a 1 microsecond of error difference, then it will lead to 0.018 degree of things. So, this means that if you like to have this meaningful comparison between two phasors at different locations, then the time axis must be same. So, there should be require a time synchronization, then only the phasors can be compared in one go. A synchro phasor, synchronized phasor, time synchronized is defined as a phasor calculated from data samples using a standard time signal as reference, using a standard time signal as reference for the measurement. Synchronized phasors from remote sites have a defined common phase. So, therefore, we say that we have a standard time signal for these two measurements. The requirement is phasors measured across power grid whole system should have a common timing reference such that direct comparison is feasible. So, from this discussion what we say that unless there is a time same time these devices have, we cannot have a meaningful comparison of these phasors as you see. So, what is that common time reference which can be achieved in a power system application perspective? That is the beauty of this so called this technology perspective. A synchronizing source that provides the common timing reference may be local or global. The synchronized signal may be distributed by broadcast or direct communication, direct connection in terms of fiber optic cable or so, and shall be reference to coordinated universal time UTC time. What the UTC time? The coordination universal time is the primary time standard by which world regulates the clock and time. So, it is within about 1 second mean solar time at 0 degree longitude. So, that reference time it must be able to provide. So, that the time information at all the measurements points should be following this UTC time. Commonly utilized synchronizing signal is the satellite signal broadcast from global positioning system GPS system, widely used in many applications. So, this is what being used in power system application also. The synchronized signals can also be disseminated by terrestrial fiber optic system. The precision time protocol PTP used to synchronize clocks throughout a computer network can achieve clock accuracy as high as sub microsecond range, which is suitable for synchronizing PMUs also. And note the GPS technology provides below 1 microsecond accuracy also. What the phasor measurement unit PMO is? As such we know this is a device and it is being conceptualized from the relaying domain, relaying area, and it has gone to many other areas of applications in power system, particularly on monitoring and control application also. So, PMO is a just like a relay device kind of thing, numerical relay kind of thing. So, it has analog inputs, anti-aliasing filters to avoid the interference of high frequency components, then A to D conversion process. So, this analog to digital gives us these samples, as you know. Now, what happens here? We have the time information of the device. For that, the time information comes from this GPS receiver with an antenna outside, where this GPS receiver receives time information from the satellite, global positioning system satellite, where atomic clocks are there, and from that atomic clocks the time information is received by this antenna every 1 second, 1 pulse, and that being is fed to the corresponding A to D converter process, where the corresponding time information of the local device, the numerical device, the measurement device is being updated or goes in accordance with this GPS based time information. The device calculates the phasors just like the relay does, rather more accurately, and so we will talk about that. And then the corresponding phase, the corresponding phasors is being provided with the time information called time tagging, and then this is being fed to the network in the system to the next destination, where the corresponding data are being used for different applications through any communication medium, in particular dedicated fiber optic or so. So, this in general 24 satellites are there, more redundant are also there on 6 orbits. Each satellite covers 42%. So, therefore, you can say that from this satellite information, the time of this device is being updated every second. As per the IEEE standard, the PMO definition is a device that produces synchronized measurements or phasors. Synchronized measurements, time synchronized, as we have already mentioned. A device that produces synchronized measurements of phasor, amplitude and phase, frequency, rate of change of frequency from voltage and current signals based on a common time source that typically is the one provided by the GPS based system, which has the UTC as the time reference. This provides the phasor along with the time tagging. Each phasor is being time tagged, the time available from this GPS based information. This time can be UTC and can be also provided by this local time information also, following the information of the available UTC. The time tag shall accurately resolve time of measurements at least 1 microsecond within a specified 100-year period. So, that should be the resolution of the time tagging. A time error of 1 microsecond corresponds to phase error of 0.022 degree for 60 Hz system, and as already mentioned 0.01 degree for 50 Hz system. In PMU, we have the synchronized phasor. The synchronized phasor is time synchronized. These phasors, voltage and current phasors, can be should be time tagged, so that the time information is embedded with the phasor data. The PMU is a function of or a logical device that provides synchro phasors, true, but beyond that also in today's applications. System frequency, rate of change of frequency already mentioned, as well as optional information such as calculated megawatts, megahertz, other measurements also, and Boolean status words like status of line and so or circuit breaker. The PMU may provide synchro phasor estimates from one or more voltage or current waveforms. Several lines may be there at a bus. So, it will scan the other lines also. The PMU can be realized as a standalone physical device or as a part of the multifunction device such as a protective relay. So, the PMU can be an independent device, or in today's context many relays are having such synchronized phasor capability. Digital fault recorder also can provide such synchronized data also, or meter also. So, these are the scopes of availing synchrophasors from such devices also, including relay, digital fault recorder, meters, or simply the dedicated PMU also. eRIGBY is a very popular format for distributing time signals in substations to different devices. Once the time information is being obtained through the antenna from the GPS antenna, from which receives every second one pulse of time information. It provides a bit, the eRIGBY system provides a bit rate of 100 PPS and a frame transmission rate in binary coded decimal BCD once per second in seconds through day of the seconds through day of the year. So, that is what the utility uses now, as of now you can say that, to provide the time informations to the such synchronized platform. How the angle is being estimated, because otherwise that will lead to improper angle reference and then it becomes purposeless application. So, we have this corresponding sinusoidal waveform. Now, we have the, let us say, cosine reference, this peak value, positive peak in this cycle. We have this UTC time reference, as already mentioned, this is available by the device, measuring device, PMU, relay also, which has the GPS antenna. So, that once it receives this, the timing of UTC time reference, at that time reference, if the corresponding time reference is ahead of the positive peak, then the angle between these two is taken as positive angle. For the representation of the phasor value, so x phasor for this wave is peak upon root 2 with angle of positive phi 1. Now, however, if the UTC time is behind the positive peak of the corresponding waveform, then the angle becomes negative between the corresponding to UTC time and the peak value of the cosine reference. So, in that case the corresponding phasor is being assigned with a negative angle. So, this approach is being used throughout the applications of the PMU concept, and it is a standard practice in this domain. The synchrophasor computes the phasor. Note, this kind of phasor estimation we have discussed in relay. Even though it is similar, the accuracy level demanded for such application is very high. We did not bother about much on the accuracy of the in the different protection element, because our speed was our more concern. Let us see this x t signal represented in terms of x m cos omega t phi, where omega 0 equals to 2 pi f 0 corresponds to the nominal frequency. Then we represent the corresponding phasor in terms of x m upon root 2 e towards j phi, and then we divide, you can say that the real and imaginary part cos phi plus j sin phi to this. So, we have an x r plus j x r for this x phasor. So, this is a real part and imaginary part. However, with x t equals to x m cos omega t phi, where omega is a general frequency which may different from this omega naught or the corresponding f naught. Also, the amplitude of the signal also may be a function of time. So, the sinusoid frequency is also a function of time f t, time varying. Then you can define delta f equals to m minus f 0. So, this if it is f t, then this will be also delta f t, delta f also changes with time. So, then you can represent this corresponding x t equals to x m t amplitude variation cos 2 pi integration of f into d t. So, this leads to, because this is omega t. So, this leads to the corresponding relations to be in terms of x m t cos 2 pi integration of f naught plus delta f, substituting this plus phi, and then 2 pi f naught t plus 2 pi integration of delta f dt plus phi. So, therefore, the corresponding x t x phasors at instant t will be x m, the corresponding peak upon root 2 e to power j 2 pi integration of delta f dt plus phi. But the delta f dt f t equals to delta f dt equals to delta f t integration of delta t, considering the delta f to be fixed within the window of observation. So, this leads to x t, the corresponding things to be x m t by root 2 e to power j 2 pi f t plus phi, and if we represent this corresponding angle in terms of psi t, then we get the corresponding frequency to be 1 by 2 pi d psi t by dt, frequency of the signal f t. Rate of change of frequency ROCF, which is also index of impotence in the system power system operation perspective. So, that becomes equals to d f t by dt. So, once we have this f t, from this angle we can get the corresponding d f by dt. Now, f t equals to f 0 plus d phi t by 2 pi t, that what we see here from this psi angle. So, that becomes equals to f 0 delta f t. So, rate of change of frequency, this becomes equal to d square d psi t by dt square equals to d f t by dt. Now, this for this we see that the corresponding PMU provides not only phasors, also provide frequency and rate of change of frequency, and we are concerned about more accuracy here. So, the PMU accuracy is being having follows certain standard, IEEE standard C 37.118A 2014 governs at what level of accuracy the PMU must have. Particularly, we are addressing on the protection application perspective. Define an index, total vector error T v is the measure of the error between the theoretical phasor value of the signal being measured and the phasor estimate, the theoretical, the true value and the estimated value. So, T v at nth instant, that becomes equals to the real part of the estimated value minus the real part of the true value square plus the imaginary part of the estimated value minus the imaginary part of the true value square upon the true value real part square plus imaginary part square. So, where x r cap in the symbol and x I cap, these are the estimates given by the PMU, and these x r and x I are the sequences of theoretical values input to the this theoretical values means the true value as we are saying. So, frequency of error f e in index like T v, error may be there in the frequency estimation. So, f true minus f measured, and that equals to, because f true is having f naught plus nominal frequency plus delta f. So, therefore, this becomes equal to delta f true minus delta f measured. So, measured is the estimated one and true value is the reference value which is known for the signal. Rate of change of frequency error RFE. So, there may be error in the rate of change of frequency also ROCF. So, that is called RFE. RFE is delta f df dt true minus df dt measured. So, the measured and true values are for the same instant of time. So, all you can say that cases are for the same instant of time. The maximum T v total vector error is 1%. So, that sees that how accurate the PMU measurement should be. The maximum FE frequency error is 0.005 hertz and the maximum RFE is 0.4 hertz per second. In the for the frequency range in the of f nominal 50 hertz or 60 hertz plus minus 2 hertz perspective. So, within that band of signal, this would have the PMU should provide a TV of 1%, frequency error of 0.05 hertz and maximum rate of change of frequency error of 0.4 hertz per second. The reporting timestamps should be examined to see the fractional seconds values or integer multiples of the reciprocal of the reporting rates. reporting rate of Fs, so 1 upon Fs rounded or truncated to the appropriate significant figure. Therefore, if Fs is 20 per second, for example, the timestamp should occur at intervals exactly 1 by 20 second or 50 millisecond per. So, further the time stamping should be done for every exact time of 1 by Fs interval. So, this means that to accomplish this kind of accuracy standard of for different measuring situations, both this is about steady state, there is a dynamic state estimation process also, for which also the corresponding TV, FE and MEX are being defined in terms of the standard. So, this requires special filtering techniques, beyond that the DFT or so what we have learned in relaying perspective. So, that for you can say that different windowing concept are being used generally, and window, rectangular window and all these things for the estimation of phasors and frequency etc. So, we see that the phasor measurement unit receives GPS time informations, scans the voltage and current samples from CT, PT or CBT from where it is being to which it is being connected, apply the DFT and all the filtering process to obtain the corresponding phasors. From the phasors it computes the symmetrical components, and it also computes the frequency and rate of change of frequency, and then the corresponding you can say that data are to be transmitted to the next destination. It has also storage for disturbance and transient recorders database storage at the local level also. This PMU reporting rate, it sends data to the different destination, like suppose we have at different buses we have PMUs in a system. This is an area where you have different buses, PMUs are there, maybe may not be in all the considered buses or so. In this diagram we have shown all the buses having PMU buses, and they are remotely placed, and these you can say the data are being they are being collected at one destination for that area. We call this as a wide area measurement systems, because it is maybe a very large area also. A system, a grid may be having several such areas where the corresponding data are being collected. Each area data again may be transmitted to different at a particular destination, a centralized destination also. Now, for this reason for a utility for the applications of such synchronized data obtained from this PMU with time information time take, generally the reporting rates to which the corresponding PMU sends, the PMU sends at a rate of these phasors with time take for 50 hertz as per the applications available in the power system, 10, 25, 50 frames per second, 60 hertz systems 10, 12, 15, 20, 30, 60 frames per second. So, such a rate is being considered followed for to be reported by these different PMUs in the system. Today, we have more powerful PMUs, they have adjustable reporting rates and they can report phasor data at a rate of 200 to 240 frames per second also for the 50 or 60 hertz system, and this gives us faster operation in control and protection domain in general. This data after computation is being stored in a transient recorder format in the PMU level, pre-triggering, during triggering and post triggering level, like any recording device for the protections and so including the relay does. Fault data are stored at several kilohertz just like the data logger or so. Now, what happens that once we have this data at one centralized location, we can plot the phasors, and this is a polar plot where all the buses angles are being plotted, and from this angle we can infer that which line or which bus is having more loaded or so, If you have such plot for the whole systems, you can have a wide area visibility where it can infer that which area is being stressed or not. Even this area having one PMU and several such area may be there, then this PMU information will reveal that the area is under stress with respect to other or not. PMU are again divided into two classes, P class for the protection class, M class for the measurement class. The P class or the protection class is fast for the fast response time, but less accurate, and M class for slow response, but of very high precision. P class is mainly for protection and control purpose, which requires fast response, minimum filtering and minimum delay, so that it can be used for the protection purposes. M class is mainly used for the measurements in the presence of out of band signals, which requires greater precision and significant filtering and allows slow response and longer delay for monitoring and metering purposes also, which is of significance at the grid level metering and so. Thus, depending upon the P or M class or the applications, the phasor filtering process is to be designed to meet the required accuracy standard and so, and the speed of operation. In the synchro phasor or the synchronous data which are being provided by these PMUs in the systems, and they have to be collected to have meaningful applications of those data. So, from different PMUs, the phasor data concentrator collects at the substation level or at the zonal level, the corresponding n number of PMU data are being collected, collated, integrated, and again it is being sent to the different next level of PDC, corporate PDC, regional PDC, and then PDC level. So, this centralized phasor data concentrator they collect the whole data, and then you can say that they are being stored in for different applications, or they are being visualized, they are being used for different applications to command, to decide through the protection arrangement and other application perspective. In Indian power grid, we have 5 areas: the southern, eastern, western, northeast and the northern region. So, these areas having their own phasor data concentrator PDC. So, these are being again connected to the National Load Dispatch Center at Delhi, where the corresponding PDC collates the data, integrates the data, aligned with the time alignment, the time information being available for each phasors through the synchro phasor technology provided by this PMU. The other history and consoles and all these things, they take this corresponding data for other applications perspective. Phasor data concentrator forms a node in a systems where phasor data from a number of PMUs or PDCs are correlated and fed out as a single stream of other applications. If it is a PDC and so it has to send to the next level of PDC, it sends as a single stream. The PDC correlates phasor data by time lag to create a system wide measurement set. So, the time tag which is being available with the each phasor is being that is being used for the by the PDC to align the corresponding different phasors, so that the measurement sets becomes better useful for the different applications on monitoring, protection and control. It performs various quality check the PDC on phasor data and inserts appropriate flags into the correlated data stream. It checks disturbance flags and records field data analysis. So, for further analysis and all these things, it performs different quality checks. It also monitors the overall measurement systems and provide a display of record performance, and so it also integrates SCADA data, and so you can say that for the energy management system applications. So, there are different standard, there is different standard for PDC also, C 37.244 for the IEEE, a function that collects phasor data and discrete event data from PMUs and possibly from other PMOs also and transmit data to other applications. PDC may buffer data for a short time period, but do not store the data. The purpose of PDC is not to store data. PDC functionality can be of several ways: data aggregations, data forwarding, data communications, data validations, all related to data, reporting rate conversions, output data conversing, redundant data handling, and so even including cyber security perspective, because these are having communication system and also the computer technology associated. The communication issue is the most challenging things here. It requires dedicated communication systems on the PMO and the wide area measurement system perspective. The channel capacity of the communication system depends upon, as you know, data rate, number of signals, voltage, currents, what are to be passed to that communication one from how many PMOs or PDC perspective. So, that will decide the channel capacity. The important aspect from the application perspective, the latency defined as the time lag between an initiating event at a source and the response of time response at some application point around, which happens to be tens of millisecond. So, point of latency talk about the late arrival of data at a destinations because of the processing and the associated communication system also. So, at different levels there are different latency in terms of the time in terms of how much millisecond of delay or so. Phasor management unit, the calculation process, acquisition of data, and so the PMO also sends data, reports data. So, therefore, associated latency also. Phasor data concentrator, it aligns the data, collects data, and then again sends the data to the next level of destination, and so wide area network, it has a communication system and then the corresponding router, and so WAM applications, wide area measurement application perspective in terms of protection, control or visibility through monitoring system also. This application software will have its own time of delay also, and then it after receiving the command, and so the execution at the control or protection level also relates to this and different device level of latency. So, overall we see that for any applications we think there are different stages of latency, and their latency should be compatible to the particular application. So, that must be checked thoroughly. The other important factor is the how many PMOs in a system for particular application also. More and more PMOs means that the visibility will be better, more inside you can see the system behavior also, but this has a greater cost associated, increased complexity to the handling the data and the ICT infrastructure. With advancement in information technology, computers and communication technology, such a voluminous data platform is feasible today. By placing an appropriate set of PMOs, reduce real time complexity, provides features of tactical value. So, it do not need to consider that all the PMOs and all these things, if you can manage with it is welcome. Sometimes the PMO data may not be available, with that situation also the corresponding application should be viable, and so in general systems can be made observable from simple observability point of view, state estimators or so. From that perspective, application perspective, a typical figure is 1/3 of the buses of a large systems, but all these depends upon how many PMOs, it depends upon the applications, whether it is for monitoring purpose, control applications or protection application. So, in overall we see that the phasor management unit, which provides time synchronized data or called synchrophasors, is a platform where wide area visibility, wide area based protection or control applications becomes viable with that kind of time synchronized data, which has also time take, time information, with the each phasor being availed. So, today most newer digital protection relays, protective relays and other digital recorders have embedded PMO functionality with the GPS antenna integrated. With synchronous data, many applications possible and we have data of the systems. So, we do not require for many applications the mathematical formulation of the system in details, no modeling, many times we do not require the modeling also for those kind of applications, because the corresponding delta angle and the corresponding phasor are being availed directly. New application scopes, there are also the technology is being moving forward, more and more revised standards are also coming up for the more stringent and accurate accuracy level, and so the technology is evolving and we will see that in tomorrow it will have more scope of applications in different domains. Thank you.